Concentrating solar thermal power plants can keep generating power when the sun goes down by using thermal storage. In Australia, there is a demand for small-scale power generation in the range of 1 to 10 megawatts to power off-grid locations at a competitive price. Currently, these communities rely mainly on diesel generators to provide energy to their homes. A 100% renewable alternative to diesel generation is to use a combination of photovoltaic cells and CST, which provide cost-effective baseload power generation.
Hi, my name is David Stevens and I'm a Senior Research Officer at the Queensland Geothermal Energy Centre of Excellence at UQ's School of Mechanical and Mining Engineering. Our centre is developing a project to build a small, concentrating solar thermal power plant at UQ's Gatton campus. This project will demonstrate hybrid PV CST power plants, but also supercritical CO2 power cycles for use in power generation across the world. My colleagues and I are designing the prototype radial turbine to use in this cycle, while the undergraduate team has been tasked with designing the surrounding power plant for this power cycle. This includes the pump, heat exchangers and cooling system, which will use the existing natural draft dry cooling tower which has already been built out at the Gatton campus.
One of the recent innovations in power cycle technology is the use of supercritical CO2 as the working fluid. When a fluid exceeds its critical temperature and pressure, it enters the supercritical region. In this state, the fluid has properties of both a gas and a liquid. It expands to completely fill the space it occupies while retaining the density of a liquid. This is beneficial for power generation as the cycle components can be more compact, efficient and cheaper compared to traditional steam cycles. As such, our power cycle will be a supercritical CO2 Rankine cycle. Some of the benefits of using CO2 as the working fluid are that it's non-toxic, non-flammable, affordable and abundant. It also has a moderate critical pressure and its thermophysical properties are well known in the supercritical area. This promises to deliver power in a safe and environmentally friendly manner. To match the inlet conditions for the turbine currently being developed, our cycle will need to include a number of components. These are a pump to raise the working fluid pressure, a recuperator to recover heat by transferring it between the hot and cold streams, a boiler and heat exchanger to test the cycle prior to connecting it to the CST, and a cooling system to get the fluid to the pump inlet conditions.
The cooling system will need to incorporate the existing natural draft dry cooling tower, as you can see behind me. We'll have to successfully integrate all of the components onto a purpose-designed skid, which will enable simple transportation of the power block.
There are several aims that we need to meet to make sure this project is a success. The main goal is to achieve a cycle efficiency of at least 35% while generating a net power output of 1 megawatt. The project is constrained by a budget of $2.5 million and the need to minimise water usage.
We're out here in Gatton, which is poised to become the first region in Australia and the world to have baseload power supplied totally by renewable technologies. This project represents a scaled demonstration of a commercially viable product. Upon its successful completion, it will serve as a proof of concept of this cutting-edge technology, inspiring further global interest into sustainable power generation.
For areas similar to this, which are faced with drought and high cost of diesel, this project demonstrates the cost-effective and feasible long-term solution. For the Gatton area in particular, the local population is growing. An expensive electricity network update has been scheduled. However, with the introduction of the CST power plant, this update can be deferred.
My role within the project is to determine how to most effectively utilise the natural draft dry cooling tower in the power cycle. I will be creating models to assess the merits of direct and indirect cooling techniques in terms of achieving the maximum heat loss from the working fluid. I will then be sourcing and integrating the components required to operate the tower.
Currently, the tower is set up to utilise indirect cooling of the working fluid. This is where water is passed through the heat exchanger bed at the base of the tower and cooled by the air. This water is then fed through an additional heat exchanger to cool the CO2. In a direct cooling configuration, the CO2 would pass directly through the tower and be cooled by the air. If this configuration is used, new heat exchangers that are suitable for supercritical CO2 would need to be sourced.
From the cooling tower, the working fluid won't be cooled enough to comply with the pump inlet conditions, therefore additional cooling of the CO2 is required.
My role is to source additional cooling that doesn't heavily reduce the cycle's efficiency and operates without wasting any water. The additional cooling system could take a number of forms, such as a chiller or a pipe network that is exposed to air or run underground. Initial research favours using a chiller, as we will be able to control its use based on the additional cooling requirements for particular ambient conditions.
A positive displacement pump has already been selected by Renrock, as it is able to discharge high pressure CO2. My role is to analyse the pump performance and integrate it into the system. I will design the inlet and outlet piping to minimise pressure loss and avoid cavitation. I am also responsible for selecting a suitable electric motor, sizing the pulsation dampeners, and performing a stress analysis on the support frame. Compared to rotodynamic pumps, positive displacement pumps have the advantage of being able to cope with high pressures, not suffering from poor efficiency at off-design conditions, and are self-priming. There are a number of design considerations for the piping, which include avoiding flanges and elbows on the run into the pump and having large enough pipes to prevent high fluid velocity, as this results in head loss.
My role is to ensure sufficient heat transfer to and from the working fluid by selecting an appropriate heat exchanger. We have been provided with a recuperator from HeatTrick, which I will analyse to determine the fluid properties at the inlet and outlet. Additionally, I will source a boiler that can be used to test the performance of the cycle independent of the thermal storage tank. The test boiler will need to be able to heat the CO2 to the turbine design inlet temperature of 565 degrees Celsius. A review of commercially available boilers has revealed that this will be a hard target to achieve, so specialist companies will need to be consulted in order to come up with a solution.
Initially, work will mainly be conducted individually within our assigned roles, while also communicating important findings and figures within the team. Once individual work has been completed, we will focus our efforts on system integration, skid and foundation design, and 3D modelling. Overall, cycle performance calculations will be carried out to optimise the efficiency. To ensure the project stays on track, we are adhering to a Gantt chart and work breakdown structure. This will enable milestones to be clearly visualised and then met. CO2 power cycles have the potential to revolutionise the way we deliver power to our communities. These new developments will hopefully replace diesel-generated electricity and act as a proof of concept for larger applications. Our undergraduate team will also work on the analysis and design of the balance of plant in order to achieve a power output of 1 megawatt and a thermal efficiency of 35%.